Based on the laws of energy conservation, energy in equals energy out. If we exercise more, increasing our energy out, whilst our energy in stays the same, in theory, you might think that would lead to weight loss. But is this really the case? Well, hello and welcome to the Cheeky Science Show, where in this video we're going to look at this recent Cell paper that shows that actually energy compensation seems to be occurring. So what does this mean for weight loss and exercise? Let us explore. So the first concept we need to understand is what is it that uses up energy in our bodies, and that's best described as our total energy expenditure. And that itself can be split up into two further categories, including activity energy expenditure, AEE, and basal energy expenditure, BEE. So for us, activity energy expenditure accounts for our physical activity, the energy used to move our muscles, etc. Whilst our basal energy expenditure includes all of the other processes like immune system function, brain function, liver function, and, well, the function of different organs that enable our bodies to function. And this last section is referred to as the thermic effect of food, which we won't talk about in this video because it's quite hard to actually calculate, so it isn't really discussed in this study. So for now, we just need to understand that total energy expenditure includes both our activity and our basal energy expenditure. So how does our total energy expenditure change when we increase our physical activity? Well, before the study, there were three main competing theories for how energy expenditure might vary with increased activity. The first one is known as the additive model. So quite simply, if you increase your activity levels, you would also increase your total energy expenditure by the same amount. And so in both these situations, the basal energy expenditure is assumed to be the same, such that if you look at these two graphs, you can see that there's no correlation between the basal and activity energy expenditure, which makes sense because in this model, the activity is seen to be independent and therefore uncorrelated. And so if there was variation in the basal energy expenditure, that would result in variation in the total energy expenditure. The second model is the performance model. And here you can see that if you increase your activity levels, that increases total energy expenditure, similarly to the additive model, but this time there's also an increase in the basal energy expenditure. So suggesting that there's greater need for metabolic machinery to support higher activity energy expenditure, and therefore predicting that the total calories burnt due to activity will be higher than just the calories used during the activity, because of additional energy spent on subsequent physical recovery and maintenance of a more expensive metabolic machinery to support this behaviour. And then the last model is the compensation model. So here, if you increase activity energy expenditure, you see that there's a decline in the basal energy expenditure such that the total energy expenditure actually stays the same. So you compensate for the increased activity by reducing the basal energy expenditure. So which strategy is it? Well, that's exactly what they try to explore in this study, as having this information will be really important for developing management strategies for weight control. And so the way that they did this is they exploited this huge data set of energy expenditure calculations that I actually discussed all about in a previous video, where they used this doubly labelled water technique to get good predictions of basal energy expenditure and total energy expenditure. And so they just had to be able to use this information to work out which model best fits the data. So this is the relationships that they could see from their data sets. And so, well, what model does it actually fit under? As it doesn't seem to fit any of the model predictions I just spent all that time talking to you about. Well, let's take a closer look at what these graphs are actually showing. So let's start with the graph on the right because it's probably easier to understand. So what we can see here is actually a negative relationship, whereby at higher activity energy expenditures, there's a lower basal energy expenditure. And so this actually fits in line with the model of energy compensation, the idea that with increased activity, there's a reduction in basal energy expenditure to compensate, to allocate that energy budget to recover from this increased physical activity. But if we then look at the graph on the left, we see that there's still a linear relationship between basal energy expenditure and total energy expenditure, which means it doesn't 100% fit the energy compensation model. And so that linear relationship is what we saw in the additive model. And well, it's also seen in the performance model. But the key difference to notice is that it's more about the strength of this correlation between BEE and TEE that's actually important, because in the data sets, they see that the correlation has a value of 0.723. So the slope is weaker than the relationship seen in the additive model. And so if the correlation equals 1, it assumes that there's no link between active and basal components of energy expenditure. But the fact that it's less than 1 suggests that there's a considerable degree of compensation occurring between the active and basal components. And so obviously we know that from looking at the graph on the right. But the fact is it's not 100% compensation. The compensation is around 27.7%. And so I tried to draw out what this model predicts based on those stacks that we saw earlier. And another way of thinking about it is that if you do a workout and it says you burnt 300 calories, so you decide to eat 300 calories of food, it is likely that you would have a net energy intake due to the energy compensation because your basal energy expenditure has declined to compensate, if that makes sense. Now, another interesting thing that they noticed in this data set is that they looked at how this energy compensation varied depending on body fatness. And what was found was that those with a lower body mass index, so the lower 10 percentile, showed a 28% energy compensation, whilst those in the upper 10 percentile had a 49% compensation. So basically, body fatness was correlating with greater energy compensation. And so in the case of someone with a BMI of 35, only about half of the calories spent on activity translate to a total daily energy expenditure. And so this is one of the important findings from the study because it has the downside that those with obesity who are trying to increase activity to lose weight may find it more challenging due to the fact that they seem to have increased energy compensation. And so the obvious question for this is, why does this happen and what are the consequences of having a reduced BEE? And why does energy compensation increase with body fatness? Is it due to genetics or does it develop as body fatness increases? Well, at the moment, these questions can't be answered from this data set. And the findings that have been shown, obviously it would be nice to see them further validated with different cohorts and taken with the same patients at multiple time points. But it certainly raises some interesting questions. John Speakman, one of the authors on this paper, has a very nice tweetorial, is that what we call them? Discussing the key highlights from this paper as well, that if you're interested in finding out some more, then I recommend you take a read through it. But anyway, I hope you've learned something in this video and understand a bit more about energy in and energy out, and how this might implicate future personalised treatment options for managing weight and exercise. So with that, I'd like to thank my Patreon supporters and thank you for listening.